Welcome back. So we've established, well, not very much about dynamic programming, but we've established the fact that it is an approach for solving some problems by breaking down a problem into smaller pieces, and then somehow reducing the amount of work we do by remembering previous pieces, blah, blah, blah. It doesn't matter at this point. Don't get caught up in that. But let's talk about how we know when we could even use it, because I've mentioned a couple times, there's only specific situations, specific problems where it works. And there's two things we have to look for. So we can use dynamic programming if we have an optimal substructure present and overlapping subproblems. I know, it sounds insane. It's a little intimidating. We're going to step through each of those in a separate video. So the first, we're going to talk about overlapping subproblems. So in order for us to use dynamic programming on a given problem, there have to be subproblems that overlap in some way. Now, what does that mean? It means that we can break one problem down into smaller pieces, but some of those pieces are reused again. They are not unique. They're reused several times. So let's take a look at an example. Fibonacci sequence. So this is something we can use dynamic programming on because it does have overlapping subproblems. So if you're not familiar with the Fibonacci sequence, it's named after this, I think, Italian guy named Fibonacci from a long time ago. And it's a sequence of numbers where every number is equal to the sum of the two previous numbers that came before it. So traditionally, it starts with 1 and 1, although nowadays, in more modern times, you'll see 0 and 1 as the first two digits. But either way, it doesn't really matter. We take the two digits that come before and add them together to get the next digit. So to derive the fourth digit, for example, we would add together the third and the second, which gives us 3. And then to get the fifth, we add the fourth and the third. So the next one is going to be 8, and then 13, and so on. So when I say the term subproblems, anytime we're trying to derive some digit, let's say the fifth Fibonacci number in the sequence, we break it down into a smaller piece, which is we take the fourth digit and add it to the third digit. We take 3 and add it to 2, and sum that together to get 5. So here's a little tree that diagrams it out. If we're trying to find the fifth number in the Fibonacci sequence, we add together the fourth and the third. But of course, to find those, we also have to add together, for example, for the fourth, the third, and the second. To find the third, we add the second and the first. Now, the second and the first we know because we start with 1 and 1. Those are the things we begin with. So we know that. So then we can say, all right, this is 1 and this is 1. This is 1 and this is 1. We add them together. This is 2. This is 2. This is 1. We keep adding together, and eventually we get 5, which is the answer. The fifth number, 1, 2, 3, 4, 5, is actually 5. Okay, so there are sub-problems here. We break down one problem into smaller steps. This is something that we often do in recursion. When we write recursive solutions, there are sub-problems involved, but that doesn't mean they overlap. So when I say overlapping sub-problems, we need to look for repetition, things where we're repeating some sub-problem. And you can see here, just to find the fifth Fibonacci number, we're calculating the third one twice, here and here, because we have to add together the fourth and the third. But to find the fourth, we have to add together the third and the second. And same thing with the second, we're calculating a couple times. First, we're calculating a couple times. And imagine that we grow this. We're trying to find the 100th Fibonacci number. There's going to be a ton of repetition, lots of subproblems that are repeated. So that's what I mean when I say overlapping. Now I'm going to show you an example of something that includes subproblems that doesn't overlap. So do you remember merge sort? Hopefully you do, where we have an array and we split it up into smaller pieces in order to sort them, and then we merge them back together. So if this is our starter array, we could split it in half and merge sort 10, 24, and we keep splitting it in half until we end up with two sorted arrays, 24 and 10. Those are sorted because there's only one item, and then we merge them together, and we get this, and then we do the right side, 76 and 73. We split it in half, sort them, merge them, and then combine them at the end. Now this involves subproblems. We're taking a bigger problem and breaking it into smaller pieces, subproblems. But there's no overlap. We're not repeating the same thing. There's no way we could reduce our duplication. If you look at it, we're sorting different pieces every time. So this is an instance of subproblems that do not overlap. No overlapping subproblems. And this structure often lends itself to the divide and conquer method, or a pattern, divide and conquer. but that's not what we're looking for. We want overlapping subproblems if we're trying to use dynamic programming. So here's a very special case where we do have overlapping subproblems with merge sort. Imagine this is our array. So we have 10, 24, 10, 24. Well, now we do the same thing, but when we split it in half, we're sorting 10, 24, and then once again, 10, 24. So we have overlap right here. We're sorting the same array, merge sorting the same subproblem. So if for some reason we had data that looked like this with a ton of repetition evenly spaced across an array, then we absolutely could use dynamic programming. It's just a very, very specific application in merge sort. Usually your data does not look like that. Okay, so that's overlapping subproblems. We have smaller pieces, they're broken down, and they have to overlap somewhere. There's some duplication of them, like we saw here, where Fibonacci of 3 is being calculated more than once. Okay, next we're going to talk about the other condition, which is something called optimal substructure.